Hello everyone. Today we're going to learn about electric circuits. We briefly, I think, talked about them the other day, and now we're just going to go through them in detail here. Okay, so a couple things to write down. For electricity to flow, the electrons, always remember electricity is electrons, the electrons need a closed path through which to travel. So the circuit can't be open. So an electric circuit provides a complete closed path for an electric current. So if we look here, this one here, this is our open circuit. And so as you can see, this is open. This was called a switch, and we'll talk more about that later. So the electricity is not going to be able to come through here because the electricity is going to come from here. It's going to get here, and then it's just going to have to stop. There's no way for it to bridge over here until that's closed. This one over here is a closed circuit, and as you can see, the electricity, the electrons are going to be able to come all the way through because there's no break in that circuit there. Now, open circuits, so you can write down this definition here. So if an open circuit, no electricity can flow. Closed circuits, you can write this one down here. When the switch is flipped, you have a complete path through which electricity can flow. So here's the difference here. So this would be an example of a very simple circuit. We've got our single dry cells. This would be like our battery. And then you've got the conducting wire leading to what's called a load. And this is the light bulb here, the load. Now the switch, this is just like your light switch essentially. It's a switch. So if we look here, when the switch is open, that one's open, no electricity can flow. So when this is switched to off, that would mean that the switch was open and no electricity can get through. And when it's turned to the on position, the electricity can go through because the circuit is now closed. Now, we're going to fill out this chart here. So we've got different terms and then symbols. So we're going to end up drawing some diagrams here. So first of all, a circuit diagram. There's no symbol for that because we're going to use all the other symbols to make them. Now the definition is schematically describes a circuit. So sometimes people don't know what schematically means. And this is just meaning diagram. So that's diagram. So schematically, this would just be a diagram that describes what a circuit is. Okay, so when you're drawing conducting wire, I'm gonna use blue here. Conducting wire is just a line. So a simple single line, that's the, oops, wrong spot. What am I thinking? I like this erase tool. So conducting wire, just a straight, well, it doesn't have to be straight though, it can be curved, but just a single line. Now, a cell. A cell is where the energy comes from, so it produces a potential difference, so a voltage. This is what's going to cause the electricity to flow. So when you go through, you're going to have it's going to have a wire, and then we're going to have a tall part, and then a short part. And then, and then the rest of the wire there. So that is what's known as a cell. One end of that is positive and one is negative. So the positive end is going to be this end here. And this is the negative end too. So the shorter bar here, that's the negative end of a cell. Now a battery is just a combination of cells. So it's a bunch of those things put together. And again, the combination of cells produces a potential difference, so a voltage. So if we are to draw that out, we're gonna have our line, because this is gonna be within a circuit. So we can have a couple of them. Well, this is actually 3 cells combined together here. And again, so we've got our positive end over here and our negative end over here. You don't need to add that in, or you don't need to draw that on a diagram, but I'm just showing you that that's how that works. Resistor or load. So this is something that's going to resist the passage of a current. So it's when you convert electrical energy into other energy forms. So this, in terms of examples, these are things like lamps, motors, your alarm clock, your phone charger, all that kind of stuff. Anything that you can plug into a wall that requires electricity is known as a resistor or a load. And the general diagram for that is just this squiggle. Okay, so you're going to have this sort of squiggly line, and that in a diagram would represent some sort of resistor or load. Now, we tend to talk about lamps a lot. So the lamp actually, even though it's a resistor or load, it gets its own symbol in a diagram. So how you're going to find it or see it, it looks like this kind of heart shape with a loop at the top, and then there's a circle around it, okay? So that is a type of resistor or load. I'm going to draw it up here a little better. Like that. You know, I think I'm not supposed to come to the... Hold on. Let's see here. Okay, so... That's better. Again, sloppy. It's hard to write with these styluses. Anyways, so that is the symbol for a lamp. And then lastly, we have switch. So a switch, and we saw one of those in our first diagram. Usually it would look like this and then continued on. So this would be a switch in an open position here. If we were to draw it in a closed position, you just kind of draw little dots to show that it's closed. I'm going to put little dots there too. Okay, so that is what's known as a switch, and it's a device for turning the electric current on and off, and it does that simply by being open or closed. So again, if it's open, that's off. If it's closed, that means that it is on. Okay, now circuit diagram. So these are some examples then, or I'm going to draw you an example of a circuit diagram. So these are our cells, right? This is our battery here. We're gonna we'll have a resistor here. Then let's put a switch here. And then let's come this way. And we're going to have a lamp. And then I'm going to come all the way around and just complete the circuit here. So this would be an example of a circuit. Remember the positive and negative ends. So if we think of it that way, the negative end is going to be on this side. Oops, can't really see that. So the electron, the path of the electrons as we move through it is going to come going this way. The electrons are always going to go from the negative end towards the positive end. So always remember that. So if this end's positive here and this end's negative, the electrons that are an excess of them that are grouping here, they're very attracted to this positive. So they're going to want to go all the way around to find that positive. Okay, so that's an example of a circuit diagram there. And the electrons are going to flow when the switch is closed, right? So that switch has to be closed in order for it to flow. Now when you draw your diagram, just draw the red parts. Just draw the red parts there, not the blue parts. Okay, flip your page over there. So the next one, it says draw this diagram using the circuit notation you have learned. So this is a circuit that's shown here. So looking at this, you need to be able to translate this kind of diagram into a schematic diagram on a circuit here. So I like to start with the cells. So I'm going to start with the battery there. So that's often how you'll see a battery drawn, but I'm going to draw it. So I'm just going to draw it with a couple. Unless it tells you how many cells are in it, you just draw it with maybe 1 or 2, 3, it doesn't matter. And then if we look here, it's going to come out the negative end, right? And then it's going to hit a switch. So right away, I have a switch. The switch goes to a lamp. So now I'm going to have a lamp here. And then it goes back. That's it. So that is, these two diagrams are equal to each other here. So they're the same thing, just drawn differently. Often circuits are drawn in rectangles, but they can be curved. It's just, we're taking here, this would be representative of real life, and we're putting it into a diagram using the circuit notation. Okay, now series circuits. Now there's two different types of circuits. So we've got series and we've got parallel. We're going to look at series first. So right away you can copy down this definition here. So series circuits are an open path for electrons to flow. So all the electrons are connected one after another. So they just follow all exactly on the same path. So there's no choices, they're just one path. Now, there is a disadvantage of this. So if there's a break anywhere in the circuit, that means no electrons will flow, which can be problematic. Examples of this would be old holiday lights. They don't really make them like this anymore, but some of you still might have some of these kicking around your houses or your homes. So some holiday lights like this, you would, if one of those bulbs goes out, all of them go out. And so then it's difficult to try and figure out which bulb is out. This is an example of three resistors or three loads in series. So here we've got our battery, of course, and then we've got 1, 2, and 3 resistors. Now every single electron that is traveling around here has to go past or go through all of those resistors. So there's no choice. There's only one path for the electrons to flow. Now, we also have what's known as parallel circuits. You know what? I need like 5 minutes. Okay, we have what's known as parallel. Sorry, I just had a conversation here. We have something called parallel circuits. So there's more than one path for the electrons to flow here. So you can copy down this diagram here. So there's choice, essentially. The advantages of this is that if one part of the circuit doesn't work, the other part of the circuit still can. So this is a much better way to have your circuits. So here are some examples here. So the lights in your home or electrical outlets, these would all be wired in parallel circuits. So as you can see, and we know this, if one light goes out, it doesn't shut the rest of the house down, right? Wiring in outlets in parallel, so these would all be in parallel here too. And this is an example, and you can copy this diagram down here, this is an example of a circuit that's in parallel. Now these are just resistors, so you can just do our other notation. It doesn't really matter. There's multiple notations for this. So as you can see, the electrons are going to come from the negative end here. They're going to travel through. So if this switch is closed, that means the circuit can work, and the electrons are going to come around. But here, part of them are going to go on this path, but some of them are going to continue around to the other. So the electrons are not going to take the same path. They've essentially got a choice, and then they're going to come back together and regroup in this section here. So you can draw that down there, and just remember, so with circuits in parallel, the electrons are going to have a path. Now, we're going to talk about the concept of resistance here. So how does resistance fit into this? Basically, the electrons are always going to take the path of least resistance. You may have heard that term before, the path of least resistance. So the electrons are going to take the easy way out, and that is always going to be true. So if we look here, so say the electrons are coming out of my cell here, and then they're coming through the switch, coming around here. Now, as it's done here, this is a series circuit, so I've got two resistors or two lights in series. So the electrons would have to go past both. Now, if I attached a conducting wire, so by a conducting wire, I just need some sort of copper wire. If I attached some wire that went around this one light bulb, the electrons would not go through here. So the electrons still would have a choice, right? Like they could either go here or through the lamp, but the conducting wire is not a resistor. It's easy for the electrons to go through. The lamp here, the load is what's known as a resistor, so there's resistance. So the electrons are not going to choose that path. They are going to choose the path of least resistance, the easier path. So they're going to bypass that one lamp and only light up the second one. So that's an example of electrons taking the path of least resistance. Okay, so 5 points to remember about current. So first one, number one, the greater the current, the brighter the glow of a lamp. So if we have more current, so again, current would be defined as charge per unit time or coulombs per second. So if we have more current, that means that the bulb is going to light up more. It's going to provide more energy. So if we look at this diagram here, this diagram on the image on the left clearly has more current going through it than the one on the right. It's a much brighter bulb. Number two, current is conserved. So what goes in one end must come out the other. So you can't just lose energy. So energy cannot be created or destroyed. It is always there. So in a closed circuit, that energy is always going to be there. Okay, you're not going to lose it. Number three, current is determined by resistance. So depending on how many resistors there are, that's going to factor in terms of how much current you have. So we've got two examples here, this with one resistor, this with two resistors. So if we say that their batteries are the same, so their cell, their source of energy is identical, this diagram here will have lower current. And that's because it's got two resistors versus the one resistor on the left. Now, two objects in a series are a larger resistance than one. So that means that if we're in series, so this circuit, this overall circuit is parallel, right? So we've got two paths for the electrons, right? They can go up here or they can come up here. But within these, this is just by itself. This one is in two. So the electrons that choose to go this path have to go past two different resistors. So what this is just saying is that because the same number of electrons are moving past both of these, but this one has two resistors to the one resistor on the left. So what this means is that this number one, this light bulb is going to be much brighter than the second one here where we've got two resistors here. So the current is going to be impacted by that. And so you'll have a larger resistance with multiple things in series. And lastly here, two objects in a parallel circuit are smaller resistance than one. So if you have, hold on one second here. Yeah, so if you have two things in parallel, it's a smaller resistance than just one thing, than if you just had one. Sorry, just one second here. Right. So two objects in a parallel circuit are smaller resistance than one, and you can see that here. So these ones are in series here, these ones are in parallel, and that's why you get the differences there. Sorry. Okay. That's it for today's lesson. Thanks, guys.